This is my Precalculus course. Today we're going to continue to learn sequences and series. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. Today we're going to learn something called sigma notation, which is used to notate sums. You can take a picture of this information if you'd like, but it's easier to show you how to do some example problems rather than to define the sigma notation in this way. So this here is a symbol that we again call sigma, and sigma is the capitalized version of our S, the English letter S, and sum starts with S. So whenever you see a sigma symbol, that means that you're going to be calculating a sum. And these numbers at the top and the bottom are the bounds of the sum. They tell you where to start the sum and where to end the sum. And the expression in here is going to tell you the pattern of the series or sum. It tells you what the algorithm is to calculate each term. So the number at the bottom is the number we plug in first. So I'm going to plug in 1 for n. So I just replaced n with 1. Then I'm going to move to the next integer. And we always use positive integers for these sums, these sigma symbols. But we don't always start with 1. As you can see down here, sometimes we start with 0. So that's something we're going to have to deal with throughout this class. So then we plug in 3. So notice we, again, are using the positive integers starting from 1 because it tells us to start from 1. But how do we know when to stop? Well, this number up here tells us to stop when we plug in 5. So now we can calculate the sum. So 3 plus 9 plus 27 plus 81 plus 243. Don't be afraid to use your calculator to find that sum is equal to 363. So again, sigma notation indicates that we're finding a sum. So let's do another example. Now we're going to first plug in 0. We're starting with 0. And then we're going to plug in each positive integer. And they have to be consecutive. You can't go from 0 to 5 or 5 to 10. It has to be 0, 1, 2, 3, 4, so on and so forth. But again, where do we stop? Well, it tells us to stop at 3. So again, 0, 1, 2, 3. And now we just do our calculations. We get 0 plus 2 plus 4 plus 6, which is equal to 12. So as you can see, this is really not that difficult. Let's try another one. So we're going to first plug in 1 to our expression. Then we're going to plug in 2. And again, the reason we plugged in 1 is because it says to start when n equals 1. And then we're going to plug in 3. And we're going to stop there because it tells us to stop at 3. So we have 4 times negative 1 to the 0 power, negative 1/2 to the 0 power, plus 4 times negative 1/2 to the 1 power, plus 4 times negative 1/2 to the 2nd power. So we have 4 times 1 plus 4 times negative 1/2 plus 4 times 1/4. And let me see if I can fit in another line. And now all we have to do is simplify. So we have 4 minus 2 plus 1. So let's just double check that, make sure we did everything correctly. Looks right. So we get 3. The sum is 3. Alright, so let's try one more of these problems before you try one on your own. So where do we start with? We start when n equals 2. So 2 times 2 plus 4, that's the first term. And then we go up to the next positive integer after 2, which is 3. So 3 times 3 plus 4. And then we go to 4. 4 times 4 plus 4. And we stop at 5, because that's the upper bound. So let's go back and make sure we wrote everything correctly. Everything looks right. So now we have 2 times 6, and you don't have to show every single step of this because these calculations are pretty easy. I'm just taking it slow so students can see exactly what's happening here. Now all we have to do is add up those numbers. So 12 plus 21 plus 32 plus 45 is 110. Okay, so I'd like you to try some of these problems now. Go ahead and attempt number 5. And when you come back, we'll do it together. Okay, we're back. So we're going to start by plugging in 1 for n. Why is that? Because there's a 1 at the bottom there. And I'm going to use parentheses. You don't have to use parentheses, but that just shows which terms we're adding. So then we're going to plug in 2, and then 3, and then we're going to stop at 4, because we have an upper bound that's equal to 4. So now let's add these together. So we have negative 2 minus 1 plus 0 plus 1, and that is equal to negative 2. If you got that right, excellent. Go ahead and try number 6, and when you come back, we'll do it together. Okay, we're back. So we're going to start by plugging in 2, and then 3, 4, 5, and then 6. Again, we got the 6 from here, and we got the 2 from there. So we have 4 plus 9 plus 16 plus 25 plus 36. So let's add those together. 4 plus 9 plus 16 plus 25 plus 36 is 90. So if you got 90, excellent. Go ahead and try number 7, and when you come back, we'll do it together. Alright, we're back. So we're going to plug in 1 for n, and then we're going to plug in 2 for n, and then we'll plug in 3 for n. So we have 3 terms. And let's simplify. So we have 1/3 times 2 to the 0 power plus 1/3 times 2 to the 1 power plus 1/3 times 2 to the second power. So that gives us 1/3 times 1 plus 2/3 plus 4/3. And 1/3 plus 2/3 is 3/3, plus 4/3 is 7/3. So the sum is 7/3. If you want to show the steps for that, you can. I don't think it's really necessary at this level of math, but if you want to go real slow, you can show each one of these steps. But again, at this level of math, you should know the basic exponent rules and arithmetic that gets us to that point. So 7/3, if you got that right, good. Try number 8, and when you come back, we'll do it together. All right, we're back. So we're going to plug in 0. And then we're going to plug in 1. And then 2. And then 3. So let's double check, make sure we wrote all that correctly. It looks right. So now we have 7 minus 0 plus 7 minus 1/4 plus 7 minus 2/4, which is 1/2, plus 7 minus 3/4. So add up all those 7s. 1, 2, 3, 4 7s, so that's 4 times 7. And then add the fractions, and we get negative 6/4. And we change that to 2/4. Add these, we get negative 3/4, and then add that one to negative 3/4, we get negative 6/4. And then 28 minus 1.5 is going to be 26.5, or you can write it as 26 1/2, however you want to write that. So if you got that one right, excellent. Okay, so in some of these problems we had arithmetic sequences. For example, here we had an arithmetic sequence, and up here we had an arithmetic sequence. And down here we had an arithmetic sequence. We also had geometric sequences here and here and here. But we didn't really need to use our formulas for the sum of the first n terms of a geometric or arithmetic sequence, simply because we could do the calculations pretty quickly just by writing the terms down. But notice here, the lower bound is 1. We're starting at n equals 1, but the upper bound is 100. So what that means is there's going to be 100 terms that we're going to have to add, and obviously we're not going to write all that out here. So in this case, we're going to use our formula for the sum of the first n terms of an arithmetic sequence. Now, how do I know that it's an arithmetic sequence? Well, I don't know, because we have to write out the first terms before we know what type of sequence it is. We may not even know if it's geometric or arithmetic. In these problems, it's going to be one or the other, but we don't know what type of sequence it is until we write out the first 3 or 4 terms at least. But this is going to end up being an arithmetic sequence, so we're going to use this formula. But in order to use the formula, we have to know what the first term is. We have to know what the common difference is. And in this case, n is actually going to be just 100. That's actually not always going to be the case, but in these problems it is, because we're starting at 1 and going to 100, so there's 100 terms. So let's plug in 1. And you don't have to show the math really, but since this is your introduction into sigma notation, I'm going to show how we're doing the calculations. So we're plugging in 1, 2, and then 3, and we'll do one more. We're plugging in 4, and we're going to keep going because the sequence doesn't end there. If I put an ellipsis, that means that it continues indefinitely, but it doesn't really continue indefinitely. It continues all the way up to 3 times 100 plus 4. And how do I know that? Well, again, the upper bound on the sigma notation is 100. So that's the last term in the sum. So let's go back and check and make sure we did all this correctly. That looks correct. So now let's simplify a little bit, because we still don't know for sure what type of sequence it is. You'll get to the point where you can look at this expression and determine whether or not it's an arithmetic or geometric sequence just by looking at that. So we have 3 plus 4 is 7, and then we have 10 and 13 and 16 and so on and so forth. So we can see exactly what type of sequence this is. 300 plus 4 is 304. This is an arithmetic sequence because we're adding a constant number each time to get to the next number. And so we know what the first term is. We know there's 100 terms because you're starting at 1 and going to 100. So now we can use our formula, because again, we're not going to add every term individually. That would take forever. So we'll use our formula, and we're adding up 100 terms. N is equal to 100. The first term is 7, and the common difference is 3. And again, n is 100. So I got that n value from here, and I got the first term that came from there, and the common difference we actually calculated. So I'll just show that. We're going very slow here, showing everything that we're doing. You don't have to show quite this much work if you don't want to, but you do have to demonstrate what the sequence is. So we're adding 3 each time, plus 3, plus 3, and plus 3. So now all we have to do is calculate. So we have the following expression. And 3 times 99 is 297. And 297 plus 14 is 311. And 311 times 50 is 15,550. So again, we needed to use the sum formula for an arithmetic sequence because there were too many terms to add one by one. Let's try another problem. And again, you're going to get to the point where you can tell just by looking at this expression whether or not the expression is arithmetic or geometric. And by the way, part of this problem is to identify whether or not the sequence is arithmetic or geometric. So we need to write arithmetic. That's part of the solution. And maybe I'll write that over here. Okay, so we don't know if this is arithmetic or geometric, so we're going to plug in some values. And it just keeps going all the way to 1/5 to the 54th power. So we have 1/5 plus 1/25 plus 125th plus 1/625th all the way to whatever that number would be, which would be very difficult to calculate. So what type of sequence is this? Well, it's just geometric because we're just multiplying by 1/5 each time, times 1/5 times 1/5 times 1/5, so on and so forth. So we'll write geometric. It's a geometric sequence, and we don't want to add up 54 terms individually, so we're going to use our sum formula for the first n terms of a geometric sequence. So that's a1 times 1 minus r to the n over 1 minus r. And we're adding up the first 54 terms. We're starting at 1 and going to 54, so we know that n is going to be 54. The first term is 1/5, and the common ratio is 1/5. They're raising to the 54th power. That's over 1 minus 1/5. So now we just have to simplify. And again, I got a1 from here, and I got that bound from there. So the sum of the first 54 terms is equal to 1/5 times 1 minus 1/5 to the 54th power, all over 4/5. And there's a lot of different ways that you could simplify this expression. I'm going to multiply both sides of the fraction by 5, both sides of the fraction at the right. So this fraction here, I'm going to multiply both sides by 5 because that's going to cancel out this 5 down here. And it's best to use parentheses in the numerator and probably the denominator. So this 5, because of the commutative rule, we can multiply and bring it over here, and it cancels out this 1/5. Again, there's a lot of different ways to do this. And this 5 cancels out that 5. You're left with 4. And there you go. That's the answer. Now, another way that you can do this is you can just, probably an easier way that I probably should have used, is you can just consider this to be multiplying one fraction by another fraction. So 1 times all this is just the same, whatever that is. And then 5 times 4/5 would just be 4. So that's another way to think about it. Again, there's different ways to do this, but this is just what popped out of my head as a gut reaction. So let's try a couple more of these before you try one on your own. So we need to see what type of sequence this is. So we're going to write the first 3 or 4 terms. And the sum goes all the way to actually we're going to be, I guess we can do that. So we can add negative 27 over 20 over 7 plus 10. That's the last term. So let's double check and make sure we did everything correctly here. Everything looks right. So let's simplify. We get 9 6/7 plus 9 5/7 plus 9 4/7, 9 3/7, and so on and so forth. And that one will be, well, we can just write it as negative 27 over 7 plus 10. We don't really care exactly what that term is. Okay, so we can see that this is obviously an arithmetic sequence. We're just subtracting 1/7 from each term. So we can say that this is an arithmetic sequence because we're just adding, or actually we're adding negative 1/7 each time, or you can say we're subtracting positive 1/7 each time. So we're going to use our sum formula for the first n terms of a arithmetic sequence. And we have 27 terms, so n is equal to 27. And the first term is 9 6/7. Normally we wouldn't want to write that as a mixed number, but it's hard to write this as a decimal, obviously. The common difference is negative 1/7, and n again is 27. Okay, so now all we have to do is simplify. So I'm going to keep that as 27 over 2 for now. And this is 9 plus 6/7, so we're actually going to use distribution. So that will be 18 plus 12/7. And we have 26. So we have 12/7 minus 26/7, which is negative 14/7. So that's actually going to be 2. So continuing to simplify, 18 minus 2. And then you can cancel here, so 16 over 2 is 8, so we're left with 27 times 8, and 27 times 8 is 216. So there's another example of a problem like that. So the 27 went there, and the first term was 9 6/7. So let's do another one of these problems. Again, you can see what the sequence is probably going to be just by looking at that expression. But let's write the first few terms out, just so we can make sure that we know exactly what the sequence is. So we have 1 minus 1, and then we have 2 minus 1, and 3 minus 1, and it doesn't look like we have a lot of room, so maybe we'll just write the first 3 terms out. And of course it keeps going all the way to 5 times negative 1.5 to the 45 minus 1. So we have 5 times negative 1.5 to the 0 power plus 5 times negative 1.5 to the first power plus 5 times negative 1.5 to the second power, and we just keep going on and on. And then we have 44th power. So let's simplify this a little bit. Again, we're just trying to figure out what type of sequence this is. So we have 5 times 1 plus 5 times negative 1.5 plus 5 times negative positive 2.25. And again, the sum goes on and on and on. So you can see that we are multiplying by negative 1.5 each time. So 5 times 1.5 is 7.5, and 5 times 2.5 is 11.25, and so on and so forth. You don't have to write quite so many terms out and show all the work here. You can probably skip this step and this step at least. But again, I'm just moving slow here so we can see exactly how to use this sigma notation. So it's hard to see exactly what's happening, but if you divide this term by this term, you get 1.5, and if you divide this term by this term, you get 1.5 again, at least negative 1.5, so it's a geometric sequence. So we'll say geometric, and now we can use our sum formula for the first n terms of a geometric sequence. That's this formula here. We learned that in the previous class. So we're adding up 45 terms. The first term is 5. I got that from there. We have 1 minus the common ratio, which is negative 1.5. And then 1 minus the common ratio in the denominator. So now let's try to simplify if we can. There may not be much that we can do to simplify. Now if you want, you can recognize that we're raising a negative to an odd power. So whatever this is going to be, it's going to end up being negative, and then you're going to subtract a negative, so it's going to become positive. You don't have to do that. If that confuses you, then that's okay. You can just leave it in that form, but technically you can get rid of those negatives. And in the bottom we have 1 plus 1.5, which is 2.5. So simplifying, we have, well, 2.5 is 5 over 2. And, well, I'm just going to bring that 2.5 out. So we have 5 over 2.5, which is obviously 2. So the final answer is 2 times 1 plus 1.5 to the 45th power. Okay, so I want you to get a picture of number 9 and 10 with your phone or a screenshot, and get a picture of 11 and 12, and I want you to try number 13. So try number 13, and when you come back we'll do it together. We don't want to add 31 terms one by one by one, so you're going to use a summation formula. But first we have to determine if this is geometric or arithmetic, so we know which formula to use. So write out the first 4 terms and figure out if it's geometric or arithmetic. Again, when you get used to these expressions, you can tell just by looking at the expression, but you may not be at that point yet. So write out the first 4 terms, figure out if it's geometric or arithmetic, and then proceed from there. When you come back, we'll do it together. Okay, we're back. So if you plug in 1, you get 4. And if you plug in 2, you get negative 8. And if you plug in 3, you get positive 16. And if you plug in 4, you get negative 32, and so on and so forth. And we go all the way to negative 2 to the 31 plus 1 power. So is this arithmetic or geometric? Obviously it's geometric, because we're multiplying by negative 2 each time. So now we're going to use our sum formula for a geometric sequence, the first n terms of a geometric sequence. So n is 31, the first term is 4, the common ratio is negative 2, so 1 minus negative 2, and let's double check, make sure we got all that right. Everything looks correct. So the sum is equal to 4 times 1, and this is an odd power. So that means when you raise a negative number to an odd power, you're just going to get another negative. So we're going to end up subtracting a negative, which means it just becomes a positive. Again, you don't have to do that. You can just leave it in this form if you want. Then we have 1 plus 2, which is 3. And we can take that 3 out and put it under the 4. That's perfectly legal. That's just a form of factoring. And we have 1 plus 2 to the 31st power. And that's your final answer. So if you got that right, good. You may have put it in a slightly different form, but there you go. So if you got that right, good. Try number 14. And when you come back, we'll do it together. Write out the first 4 terms and determine if it's arithmetic or geometric, and then you know what formula to use. Alright, we're back. So we're going to plug in 1, and we get 3. Plug in 2, and we get 4. Plug in 3, and we get 5. Plug in 4, and we get 6, and so on and so forth. So you can see that this is obviously an arithmetic sequence. And the last term would be 2 plus 40. So we need to write arithmetic. If you can do the math in your head, then you can save yourself a lot of time, because most of the time that we were taking to do these previous problems was just showing all the work. You don't need to show that work. So because this is arithmetic, obviously we're going to use our sum formula for the first n terms of an arithmetic sequence, and we're adding up the first 40 terms. So n is equal to 40. The first term in the sequence is 3. The common difference is 1. And again, n is 40. So now all we have to do is simplify. So we have 20 times 6 plus 1 times 39. 20 times 6 plus 39 would be 45. Do the math and you get 900. So if you got that right, excellent. Alright, I want you to try number 15. Write out the first 3 or 4 terms. Probably good to write at least 4 terms. Determine if this series is geometric or arithmetic, and then use the appropriate formula. When you come back, we'll do it together. Alright, we're back, so plug in 1 for n, and you get 1.2. Plug in 2 for n, and maybe I should show this. So plug in 1 for n, 2 for n, 3 for n, and then 4 for n. And it's not enough to stop there. We have to write what the last term is, because if we write an ellipsis, that means that the sum goes on forever, and that's not really true. It doesn't go on forever. It stops at 2 times 0.6 to the 10th power. Okay, so we get 1.2, and 0.6 times 0.6 is 0.36, and times that by 2 we get 0.72. But you don't really need to write the next step out necessarily in order to figure out if it's geometric or arithmetic, because we can see just by looking at all these expressions that it's got to be geometric. But the next term is going to be 0.432, and the next term is going to be 0.2592, and then we don't really care what that value is, because that's going to be too hard to calculate, or too hard to write it down. So if you if you divide this term by this term, you get 0.6. If you divide this term by this term, you get 0.6. If you divide this term by this term, you get 0.6. So it's got to be a geometric sequence because you're multiplying by some constant term that we call the common ratio to get the next terms. So that means that we're going to use our formula for the sum of the first n terms of a geometric sequence. And we're adding up 10 terms, and the first term is 1.2. So I got that from there. And the common ratio is 0.6, and we can actually see the common ratio in the expression. Again, if you do enough of these problems, you'll get to the point where you can see it's geometric just by looking at this expression. So 1 minus 0.6 in the denominator, and now we'll see if we can simplify. So the denominator is going to become 0.4. It's probably best to put that 1.2 in parentheses just to be safe. And then we can take the 0.4 out. Some teachers may say that it's not really even necessary to simplify beyond this point. But if you can combine these, it's really best to do that. 1.2 divided by 0.4 is 3, because 0.4 goes into 1.2 3 times. And you can see that this is a much simpler form to write our answer in. So if you got that right, excellent. So I'd like you to try one more of these problems before we go on to something else. And when you come back, we'll do it together. Write out the first 4 terms, determine if it's arithmetic or geometric, and then use the appropriate formula. When you come back, we'll do it together. Okay, we're back, so I'm going to plug in 1, and I get negative 11. And I'm going to plug in 2, and I get negative 13. And I'll plug in 3, and get negative 15, and 4, and we get negative 17. And then the last term is going to be negative 2 times 65 minus 9. So you can see that this is obviously an arithmetic sequence. We're just subtracting, or we're subtracting 2, or you could say we're adding negative 2 each time. So we're going to use the sum formula for the first n terms of an arithmetic sequence. And the first term is negative 11, and n is going to be 65. So we're adding the first 65 terms. The first term is negative 11. The common difference is negative 2. And so all we have to do is simplify this expression. So I'm going to leave that as 65 over 2 because I have a feeling that 2 is going to cancel out. It might not. So we get negative 22 minus 2 times 64. Be sure to write enough parentheses there. And so we have we have 65 over 2 times negative 22 minus 2 times 64. So that's going to be negative 22 minus 128. And we get negative 150. So 150 divided by 2 is negative 75. There's a lot of different ways that you can do this. So we have 65 times negative 75, and that is negative 4,875. So if you got that right, excellent. So that is the sum of that arithmetic sequence. Okay, so now we're going to go to a slightly different variation of these problems. In all the previous problems, the lower bound was always n equals 1. N equals 1, n equals 1. Look at all these problems. N was always equal to 1 in these problems that we did where we had to use a formula for the nth term, the first, or the formula for the first n terms of a geometric or arithmetic series. That was not the case with these first problems, but we weren't really using the formula. But the last 8 problems that we did, n was always 1. That was the lower bound, as you see up here. But in this problem, the lower bound is not 1. It's 0. So that complicates things. So when we add all the terms using our formula, we have to be very careful because 20 is not going to be n. And I want you to see these types of problems so that you can be aware that you have to really stop and understand exactly how you're using the formula. So what we're going to do is find, again, the first 4 terms. And we don't have time to show all the math because we have quite a few problems to do here. So I'm going to rush through this. We're going to plug in 0 for n. Then we're going to plug in 1 for n. And then we're going to plug in 2 for n. So then we get 9 over 3,000. And that's going to reduce to 3 over 1,000. And so on and so forth. The last term is going to be 1 over 1,000 times 3 to the 20th. So 1 over 3,000 times 3 to the 20th is the last term. So this is obviously an arithmetic sequence. We can see just by looking at the expression because we're multiplying by 3 each time. It may actually be better to keep these expressions in the non-reduced form. So that would be 3 over 3,000 and 9 over 3,000, and you can see again we're just multiplying by 3 each time. So this is a geometric sequence, and we're going to use our formula for the first n term, the sum of the first n terms of a geometric sequence. So that's Sn is equal to the first term times 1 minus the common ratio to the nth power over 1 minus the common ratio. But here's where we have to be careful. In all the previous problems, n was the upper bound. That's not going to be the case. because there's not 20 terms. If there were 20 terms, n would be 20. But in this case, there's actually 21 terms. Okay, this number is not n. 21 is n. Why is that? Well, if you start at 1, you have 1, 2, 3, 4, all the way to 20 terms. You have a total of 20 terms if we're just writing the numbers of each term. But you're starting at 0. So you have these 20 terms, but you also have the 0 term. This blue number here is the 0 term. So there's actually a total of 21 terms. So I'm going to write that. Those add up to 21. And maybe I'll write that at the bottom. So n equals 21 terms. So we're finding s subscript 21, not s subscript 20. The first term is 1 over 3,000. The common ratio is 3. Again, n is 21. And so all we have to do is simplify that expression. So we have 1 over 3,000 times 1 minus 3 to the 21st power all over negative 2. So we're going to have to use an arrow because we're out of room. That's okay. I'm going to take that negative 2 out and put it into the fractions. So we have negative 1 over 6,000 times 1 minus 3 to the 21st power. We could just write it as this form here. That's fine. That's probably better. And so that is the sum of those 21 terms. Again, it's not 20 terms, it's 21 terms. So I know that's kind of confusing, but those are the types of problems that we're going to be doing now, where it's not exactly obvious what n is going to be. So here's another example. We're not starting at n equals 1, we're starting at n equals 2. So there's not going to be 34 terms. There's actually going to be 33 terms, one less. If you're starting at n equals 1, there's 34 terms. If you're starting at n equals 0, there's 35 terms. And if you're starting at n equals 2, there's 33 terms. So it's very confusing. Let's write out the first terms. So we have negative 3 as the first term. If you plug in 2, you get negative 3. Plug in 3, you get negative 7. And plug in negative 4, or plug in positive 4, that is, and you get negative 11. And plug in 5, and you get negative 15. And on and on and on. So the last term would be negative 4 times 34 plus 5. So this is obviously an arithmetic sequence. So we can use our formula for the sum of the first n terms of an arithmetic sequence. Now, again, the hardest part here is to figure out what n is. How many terms are we adding? And again, we're going to be adding 33 terms, not 34, not 35, but 33. So it's going to be a total of 33 terms. And the first term we obviously know is negative 3 because we wrote out the list. That was the whole purpose of writing that list, is we can see precisely what the first term is and the common difference. So it looks like we're subtracting 4 each time, so the common difference is 4. And again, n is 33. So now all we have to do is simplify that. So we have negative 6, and we're going to get negative 4 times 32. So that'll be negative 128. And then we get 33 over 2 is times negative 134. And if we simplify that, we get 33 times negative 67. 134 divided by 2 is 67, and 67, negative 67 times 33 is negative 2,201. So there you go. So again, the difficulty of that problem is knowing exactly how many terms we're adding up, and that's going to be n. N was not 34 in that problem. You have to be very careful when you use those sum formulas with the sigma notation. Let's try another one of these, and we'll try to pick up the pace here a little bit. So plug in 3, we have 9. Plug in 4, we have 12. Plug in 5, we have 15. And you can see what this is going to be. Then we plug in, lastly, 28. Guess we don't need double parentheses on that. So this is obviously arithmetic, and we're going to use this familiar formula for the sum of the first n terms of an arithmetic sequence. The question is, what is n going to be? How many terms are we adding? We're not adding 28 terms. That would be if n was equal to 1. We're not adding 27 terms. That's if n is equal to 2. We're not adding 29 terms. That's if n were equal to 0. We're going to be adding 26 terms because n is equal to 3. So you can count the terms if you want. Think about the logic of that. Again, if n were 1, we'd be counting 1, 2, 3, 4, 5, all the way to 28 terms. So that was a total of 28. If we're starting at n equals 2, we're counting 27 terms, and if we start at 3, we're counting 26 terms. So starting from here, we see that n is actually equal to 26, and we don't care about those. We'll just cross those out. So we're adding 26 terms. We have 26 over 2 times the first term, which is 9, plus the common difference, which is obviously 3 times 26 minus 1. And again, we got that a1 from there. So let's simplify. We have 13 times 18 plus 3 times 25, and so that's 75 plus 18, which is 93. You don't have to show every single one of these steps. You do have to show the formula you're using, but I'm showing a lot more steps than is really necessary when it comes to the arithmetic and algebra, just because I want students to see exactly what is happening in these formulas. So 1,209. So we've done 3 of those problems where it's not exactly obvious how many terms we're adding up. So here's another example where it looks like we're adding 16 terms, but we're actually adding 17 because the 0 term counts as a term. So we have negative 0.9, When you plug in 0 for n, you get negative 0.9. When you plug in 1 for n, you get positive 0.81. And when you plug in 2 for n, you get negative 0.729, and on. The last term would be negative 0.99 to the 16 plus 1 power. So the first term is negative 0.9. This is obviously geometric because we're just multiplying by negative 0.9 each time. And our formula for the sum of the first n terms of a geometric sequence is the following. Now again, the most important part of this problem is to figure out what n is equal to. If n were equal to 1 in the lower bound, then there would be 16 terms exactly, but because we're starting at 0, there's actually going to be 17 terms. So the first term is negative 0.9. The common ratio is negative 0.9 and is 17. And the common ratio again is negative 0.9. So now all we have to do is just simplify that. And so we get 1.9 in the denominator. And again, this is an odd power. Just so happens that we're getting the same types of problems where we can actually simplify that to a positive and just make that a positive base. Every problem that we've got so far just happens to have that characteristic. Now if this were an even power, you could get rid of this negative, but you could not get rid of that negative. So let's just simplify this. So let's see what we get when we divide 0.9 by 1.9. I'm just going to bring that 1.9 out to make things look nice and neat. So don't be afraid to use your calculator. 0.9 divided by 1.9 is a really nasty number, so we can't do that. So let's multiply both sides of this fraction by 10, and then we get negative 9 over 19. That'll make it look nice and neat. So that is the sum. Okay, so again, the most important thing with these problems that we've been doing is to determine what n is going to be in your formula. Don't be deceived. N is not going to be the upper bound necessarily in these problems we're about to do. It's not 16 for this example, it was 17. And again, the reason for that is because we have all these terms all the way up to 16, which means there's 16 terms, but that's not including the 0 term. We start with n equals 0, so there's actually a total of n equals 17 terms, not 16. So you have to be really careful about that. So I want you to try number 21. You can use 20 to help you and get pictures of these previous problems if you haven't already done so. And when you come back, we'll do it together. Alright, we're back. So if n equals 4, you've got that term, and if n equals 5, you've got that term, and if n equals 6, you've got that term, and 7, you've got that term, and so on and so forth. So we have to write the last term, which is 300 over 5. So this is obviously looks like this is a arithmetic sequence where we are adding 1/5 each time. So we're going to use our formula for the sum of the first n terms of an arithmetic sequence. The question is, what is n? Is n equal to 300? Are we adding 300 terms? Nope, we're not adding 300 terms. If n equals 1 in the bottom bound, then we're adding 300 terms. If it's 2, we're adding 299 terms. If it's 3, we're adding 298 terms. And if it's 4, we're adding 297 terms. So n is actually going to be 297. I know that seems weird, but again, that's just something you have to be careful of when you're doing these types of problems. The common difference is obviously 1/5. You're just adding 1/5 each time. And all we have to do is just simplify this math. So we get 297 over 2 times 8/5 plus 296 over 5, and that would be 304 over 5 times 297 over 2, and let's do the math. So 297 times 304 is 90,288, and don't be afraid to use your calculator, obviously. So then we're going to divide that by 10, and it looks like this is a manageable number. It's 9,028.8. So if you got that right, excellent. Again, the hardest part is to figure out what n is going to be. In this case, it was 297. Go ahead and try number 22. When you come back, we'll do it together. Alright, we're back. So if you plug in 2 for n, you get -2. If you plug in 3 for n, you get 4. If you plug in 4 for n, you get -8, then +16, and so on and so forth. So this is a recognizable series. And of course, in the last term, you want to plug in 49. So this is obviously a geometric sequence, and we're going to use this formula here, and the question is, how many terms are we adding? If n were equal to 1, we'd be adding 49 terms. But because it's equal to 2, we're adding 48 terms. So n is 48. The first term is obviously -2. So we have 1 minus the common ratio, which is -2 to the 48th power, over 1 minus -2. And so we got that a1 value from there, and we should probably put that in parentheses just to be safe. So we have now we have a case where we're raising to an even power. Now you can leave it in this form if you want, but because that's an even power, that means when you raise this -2, the result is going to be positive. So you can just get rid of that negative and say 2 to the 48. Now again, if that confuses you, then just forget about it. Just leave it in this form. That's fine. In the homework, I'll give you both forms so it doesn't confuse you. So now we can take that 3 out, and we can put it in front to make things look nice and neat, and that is the final answer. So you may have your answer in a slightly different form, but that's okay, as long as when you do the math, it works out. So I want you to try number 23, determine if it's arithmetic or geometric, And then remember, the hardest part is to figure out what n is going to be in the formula. So try 23. When you come back, we'll do it together. Okay, we're back. So if you plug in 0, you get 10. Plug in 1, you get 4. Plug in 2, you get negative 2. Plug in 3, you get negative 8. And so on and so forth. The last term you're going to plug in would be negative 6 times 21 plus 10. So this is obviously arithmetic series, and so we're going to use our formula for the sum of the first n terms of an arithmetic sequence. And again, the big question is, what is n going to be? Well, if the lower bound was n equals 1, then it would be 21 terms. But since it's 0, it's going to be 22 terms. And the common difference looks like it's going to be negative 6. So now we have 11 times 20 minus 6 times 21, which is 126. And 20 minus 126 is negative 106. Negative 106 times 11 is negative 1,166. So if you got that right, excellent. Okay. So I want you to try one more of these types of problems. Again, the hardest part is to figure out what n is going to be equal to in your formula. So try number 24. When you come back, we'll do it together. Alright, we're back. So we plug in 3. We get 2 over 125. Plug in 4, you get 2 over 625. Plug in 5, you get 2 over 3,125, and so on and so forth. The last term is going to be 2 times 1/5 to the 44th power. So we can see that we're just multiplying by 1/5 each time, and it's a geometric sequence. So we're going to use our sum formula for the first n terms of a geometric sequence. The big question is, what is n going to be? How many terms are you adding? You're not adding 44. If the lower bound were n equals 1, it would be 44 terms. If it were 2, it would be 43 terms. And because it's 3, it's going to be 42 terms. So we're adding up actually 42 terms. And the first term is 2 over 125. The common ratio is 1/5. Adding up 42 terms. And in the bottom we have 1 minus 1/5. Okay, so that simplifies to 4/5 in the denominator. And so I'm going to multiply these two, and if we do that, we get 12 in the denominator. A lot of different ways to think about how to simplify this expression. but we end up with 1 over 6. And you can just combine that to one expression and say 1 minus 1/5 to the 42nd power all over 6. There you go. So if you got that right, excellent. Okay, so now we're going to go to some some other situations here. So I'm going to plug in 1 and we get 0. This is what's different about these problems we're about to do, is the first term seems to be 0, so that kind of complicates things a little bit. Then we're going to plug in 2 and we get 1/2. Then we'll plug in 3 and we get 1, and plug in 4 and we get 1 and 1/2, and it's obvious what's happening here. The last term will be whatever 1/2 times 24 minus 1/2 is. So we're just adding 1/2, so obviously this is an arithmetic sequence, arithmetic series that is. And so we're going to add the first n terms using our formula. But there's something that's pretty confusing here. Should we consider 0 to be the first term, or should we consider 1/2 to be the first term? I mean, 0 is not really a term, right? It's nothing. Well, the truth is we could consider it to be the first term. 0 can be a term, but we could also consider this to be the first term. So which one do we want to use? Well, we can use either. If the first term is 0, then n would be 24. Because when you plug in 1, you get 0. That's the first term. So there's obviously going to be 24 terms, because we're starting at 1 and going to 24. 24 terms if A1 is 0. But if the first term is 1/2, because we can also do it that way, we can consider this to be the first term, then n would be 23. Because if we're starting here, this is not a term that we care about. So we're going to start here and add all these terms, and that's going to be a total of 23, because remember, the first term, n equals 1, was 0, so we're actually starting at n equals 2, and if we're going from 2 to 24, then there's actually 23 terms. So you can do it either way. And what we'll do is we'll actually do it both ways, just to show you that you're going to get the same answer regardless. So let's try n equals 24. And the first term would be 0. That's if we're considering the first term to be 0. So the common difference is 1/2. N is 24. And we'll see what we get. So we have 12 times 0 plus 23 over 2. And we end up getting 138. Alright, so now let's do it the other way. Let's consider 1/2 to be the first term. So then we're going to add up 23 terms. And that's going to be 23 over 2 times 2 times the first term, which is actually 1/2, because we're considering this to be the first term now. We're just ignoring 0. Plus the common difference times 23 minus 1. So let me move that out of the way. So let's simplify this. So we have 23 over 2 times 1 plus, that will be 11. And so we have 23 over 2 times 12, which is 6 times 23, which is 138. So you see we got the same answer. So just be aware you can do it either way. I think to keep things simple, we probably just want to consider 0 to be the first term. But you can do it any way you want to do it. So let's try another one of these. So if we plug in 1, we get 0 for the first term again. Plug in 2, and you get -1. And plug in 3, and you get -2, -3, and so on and so forth. And the last term would be -67 plus 1. So this is obviously an arithmetic sequence. And we can consider this to be the first term, or we can consider this to be the first term, but I'm going to make 0 the first term. And so what that means is let me write the formula. And you're probably wondering if you have to write these formulas every time you do this. Well, it's good to help you memorize the formula, so I would say yes. You probably want to write the formula every time, and it shows the viewer what formula you're using, what tool you're using. So you really need to write the formulas. So we're adding 67 terms, and the first term is 0. So plug in 0 there, and then the common difference is -1. So we have 67 over 2 times 0 minus 66. Sorry. Remember, always write nice and neat. So then we have 67 over 2 times -66. And let's do that in the calculator. So we have 2,211, -2,211. So again, what's different about these problems is that the first term is 0, and that complicates things. A lot of students get confused by that because they don't know if they're supposed to consider 0 to be the first term or -1 to be the first term. Well, you can do it either way. The difference is n is going to be different. If 0 is the first term, n is 67. If -1 is the first term, then n is going to be 66. So you have to be careful about that. So I want you to take a picture of number 25 and number 26. Well, you can keep 26 in the window and go ahead and try 27. What's different about this problem is that 0 is going to be our first term. So you have to make sure that you're using this formula correctly and understand that there's two different ways to use it. When you come back, we'll do it together. Alright, we're back, so we're going to plug in 1 for n, and we get 0. Then we're going to plug in 2 for n, and then we get 3. Plug in 3 for n, and we get 6. And 4 for n, and we get 9, and we just keep going and going and going. Okay, so obviously this is arithmetic. So we're going to use our formula for the sum of the first n terms of an arithmetic sequence. And the question is, are we going to let this be the first term or this? Well, I'm going to let 0 be the first term. I'm always going to do it that way. So that means there's 38 terms total. The first term is 0. The common difference is obviously 3. So we have 19 times 0 plus 3 times 37. And 3 times 37 is 111. Multiply that by 19 and we get 2,109. So if you got that right, excellent. Try number 28. Remember, I'm considering 0 to be the first term. So that means there's going to be 18 terms total. N is equal to 18. So try number 28. When you come back, we'll do it together. Okay, we're back. So if you plug in 1, you get 0. If you plug in 2, you get 9/2 minus 2. And if you plug in 3, you get 5. So these are kind of strange terms. Plug in 4, you get 19 over 2 minus 2, and so on and so forth. So it's a little difficult to see the pattern. Last number I'm going to plug in is 18. So that's the last term there. So again, it's kind of difficult to see exactly what's happening here. So let's simplify a little bit. We have 5/2 and then 5 and then 15/2 and so on and so forth. So the last term would be that would be 89 over 2 minus 2. So it looks like we're adding 2.5 each time. We can see if we change to a decimal. 2.5 plus 2.5 is 5, plus 2.5 is 7.5, and so on and so forth. And the last term would be 43.5. Not that we really care about the last term. Actually, that would be 42.5. Okay, so we can see that this is an arithmetic sequence. It was kind of difficult to see that, but now we know. So we're going to find the sum using our formula for the sum of the first n terms of an arithmetic sequence. And the question is, are we going to let 0 be the first term or 2.5? Well, I'm going to let 0 be the first term. That means we're adding 18 terms. If we let 2.5 be the first term, then we're going to add 17 terms. So just be aware of that. The first term is 0. The common difference is 2.5. And then we get 9 times 0 plus 2.5 times 17. And 2.5 times 17 is 42.5. And multiply that by 9 and we get 382.5. So if you got that right, excellent. Okay, so now we're going on to problems that are a little bit more confusing in the sense that the first term is going to be 0, just like we did in the previous problems. And writing some other terms here, we can see that the sequence is going to be arithmetic. The last term is going to be 80 minus 2. But again, the big question is, should we consider 0 to be the first term or 1? Well, I'm always going to consider 0 to be the first term. If 0 is the first term, if 0 is the first term and n were equal to 1, then we'd have 80 terms that we're adding. Okay, but the problem is n is not equal to 1, n is equal to 2 in the lower bound. So if n is equal to 1, we're adding 80 terms, but if if n is equal to 2, then we're actually adding 79 terms. So again, if the first term is 0, we're adding 79 terms. If the first term is 0, we're adding 79 terms. But if this term, if 1 were the first term, we'd actually be adding 78 terms. So you have to be careful about that. So we have 79 over 2 times 0 plus 78, and 78 times 79 divided by 2 is 3081. Okay, so that is a source of confusion. How many terms are there, and what should n be in our sum formulas? That's an issue we have to deal with. So let's plug in 0, we get 0, plug in 1, plug in 2, and you can see what's happening here. It's an arithmetic sequence, and the last term is going to be 75 over 3. So it's an arithmetic sequence, and so we're going to be using our formula for the sum of the first n terms of an arithmetic sequence. Now, if 0 is the first term and n were equal to 1, then there'd be 75 terms, 0 being counted as one of the terms. But because the lower bound is 0, there's going to be 76 terms. And again, 0 is the first term. I know that's really confusing, but that's why we're doing these problems. So I want you to get practice with using this formula, making sure that you're using it correctly. So again, I'm making the first term 0. Common difference is obviously 1/3. So 76 divided by 2 is 38, and 75 divided by 3 is 25, so 38 times 25 is 950. So again, we have another problem where things get kind of confusing. Let's try this one. Plug in 3, and 0 is the first term again. Then we'll plug in 4, and we get -2. Plug in 5, and we get -4. Plug in 6, and we get -6, and so on and so forth. Last term is going to be 6 minus 2 times 22. So this is obviously arithmetic. And we're going to use the same formula for the sum of the first n terms of an arithmetic sequence. The question is, what is n going to be? Well, it depends. Are you going to make 0 the first term, or are you going to make -2 the first term? You can decide. I always make 0 the first term. Now, if 0 is the first term and n were equal to 1 in the lower bound, then there would be 22 terms. The problem is n is not equal to 1. N is equal to 3. So instead of there being 22 terms, there's going to be 20 terms, again, with 0 as the first term. So we're adding up 20 terms. The first term is 0. The common difference is -2. And so we have 10 times 0 minus 38. And so final answer is -380. So you can take a picture of number 29 and 30 and 31, and that'll help you to do number 32. So again, what's different about these problems is that the first term is 0, and you can count 0 as the first term if you want, or you can count the second term as the first term. It's up to you, but I would just make 0 the first term, and then use your head to figure out how many terms there's going to be. If 0 is the first term, then is there going to be 13 terms total? Is n going to be equal to 13 in your formula? Or is n going to be equal to 14? Or is it going to be equal to 12? How many terms are you adding? So go ahead and try 32, and when you come back, we'll do it together. Okay, we're back, so let's find a few of the terms here. We can see that this is obviously going to be an arithmetic sequence. The last term is 4 times 13. And let's write the formula. So how many terms are there going to be? Well, if we consider 0 to be the first term and n were equal to 1, then there'd be a total of 13 terms. But because n is 0, there's going to be 14 terms. So we're adding 14 terms. Whoops. And the first term is 0, and the common difference is 4. So we have 7 times 0 plus 4 times 13, which is 52. And 52 times 7 is 364. So if you got that one right, excellent. Okay, so I want you to try number 33. Remember, the hardest part is figuring out what n is going to be in your formula. So try 33, and when you come back, we'll do it together. All right, we're back. So if you plug in 2 for n, we get 0. If you plug in 3 for n, we get 2/3. It may take a second to do the math on some of this. If we plug in 4 for n, and we get 4/3, and we plug in 5 for n, and we get 6/3, and we plug in 6 for n, and we get 8/3, and you can see what's happening. And the last term is going to be 2 times 17 over 3 minus 4/3, whatever that ends up being. So we can see that this is arithmetic, and we use our formula. And the question is, what is n going to be equal to? Well, we're considering 0 to be the first term, And if n were 1 in the lower bound, there'd be 17 terms. But because it's 2, there's going to be 16 terms. And again, the first term is 0. The common difference is 2/3. We have 16 minus 1. So then we have 8 times 0 plus 10. And that's going to be a total of 80. So if you got that right, perfect. Okay, on to 34. The first term is going to be 0. And I forgot to write an upper bound here. Let's say that that's going to be, maybe we'll choose 100. Yeah, let's choose 100. So when you come back, we'll do it together. Okay, we're back. So if you plug in 3, you get 0. If you plug in 4, you get negative 1/4. And if you plug in 5, you get negative 2/4. Plug in 6, and you get negative 3/4. Plug in 7, and you get negative 4/4, and you can see what's happening here. Again, in this case, it's easier not to simplify the fractions. Then you plug in 100 for the last term. And I'm just using parentheses to show that those numbers are all one term. So obviously this is arithmetic. And we'll use our formula. So the question is, what is n going to be? Well, if we consider 0 to be the first term, if n equaled 1, we'd have 100 terms. If it were 2, we'd have 99 terms, but because it's 3, we're going to have 98 terms. So we're adding a total of 98 terms. I know that's confusing. 0 is the first term. And you can see that we're just subtracting 1/4 each time. That's the common difference. So 98 divided by 2 is 49. And we have 0 minus 97/4. And then we have 49 times 97/4. And whoops, I forgot to write a negative on that fraction. So 49 times negative 97, and then divided by 4 would be negative 1,188.25. So if you got that answer, excellent. So now we're going to calculate the values of infinite geometric series. So we know that this is an infinite geometric series because we have the 8 turned on its side up here. That means we're going to add all the terms. So what are the terms? Well, they're going to be 3/7, 3/7 squared, 3/7 cubed, and it's going to continue indefinitely because it's an infinite series. There's an infinite number of terms. And you can see that this is geometric because we're just multiplying by 3/7 each time, so the common ratio is 3/7. The first term in the sequence is 3/7. So what that means is we can use our formula for an infinite geometric series where r is between -1 and 1. So maybe we'll write that just to show r must be between -1 and 1, and we confirmed that that's true. 3/7 is between -1 and 1. So that means we can use this formula. So the first term is 3/7. The common ratio is also 3/7. So we have 3/7 over 4/7, which simplifies to 3/4. So believe it or not, we added all of the terms, an infinite number of terms, and the sum is 3/4. And you can simplify this however you want to. That's a complex fraction, so you can write 3/7 divided by 4/7 and then do the math that way, or you can do the math in your head and multiply both sides by 7, both sides of the fraction, using the fundamental principle of fractions, and the 7's cancel out. So let's try another one of these. Let's write out the first few terms. So if n is 1, we have 10 times -5/6. If n is, n is 0 is the first, it gives us the first term, and then if n is 1, we have 10 times -5/6 squared. And if n is 2, we have 10 times -5/6 cubed, and so on and so forth. It continues indefinitely. So a1, the first term, is 10 times -5/6, which is just -50/6, which is -25/3 if you want to simplify it. So we have the first term, and r, the common ratio, is obviously -5/6. Just multiplying by -5/6 each time. So because r is between 1 and -1, we can find the sum of all of the terms. Even though there's an infinite number of terms, we can find the sum. Now I think I'll put a check mark here, showing that we confirmed that r is between 1 and -1. We'll do that down here also. So let's use our formula. Our formula for the sum of the infinite number of terms in a geometric sequence is the first term over 1 minus the common ratio. And the first term is -25/3. We found that up here. And the common ratio is -5/6. So all we have to do is simplify that. And we have 1 plus 5/6, which is 11/6. And again, there's a lot of different ways to simplify a complex fraction in your head. But the easiest way is really just to multiply both sides of the fraction by 6, and we get 11 in the denominator and -50 in the numerator. So we added an infinite number of terms and got -50/11. Okay, let's try another one. So let's plug in 2 to find the first term, and we'll plug in 3 to find the second term, and then 4 to find the third term, and so on and so forth. You can see that this is a geometric sequence, and the common ratio is r. The first term is 2, or the common ratio is 2, but notice that r has to be between -1 and 1, and 2 is not between -1 and 1. So we write, we can write that those inequalities are not true, or we can just say because r equals 2 is not between -1 and 1, the sum does not exist. And that is our answer. Alright, go ahead and try number 38. You can use 35, take a picture of 35, and you can use 36 and 37 to help you. When you come back, we'll do it together. Okay, we're back. Let's plug in some numbers just so we can get a feel for what type of sequence we have. You can see that this is a geometric sequence, obviously, or geometric series, and it continues indefinitely because we have an infinity symbol. So we need to consider the first term. That's obviously 1, and the common ratio we can see is obviously -1/3, and the common ratio in this case is between -1 and 1. So what that means is we can find the sum. The sum actually does exist, even though there's an infinite number of terms. So let's use our formula. The sum is the first term over 1 minus the common ratio, and the first term is 1, and the common ratio is -1/3. So let's simplify. We have 1 over 1 plus 1/3, and we're out of space, so we can use an arrow. We have 1 over 4/3, and if you do the simplifying on that, we end up with 3/4. So believe it or not, the sum of all the infinite number of terms is 3/4, because the sum does what we call converging. It converges. So if you got that answer, good job. Go ahead and try number 39. I'll leave 38 in the window. When you come back, we'll do it together. Okay, we're back. So you may have been a little confused by this, but just to make sure that you know exactly what's happening, we have -0.8, and then we have -0.64. So notice that the sign didn't change, because -0.8 to the n is the same thing as -1 times 0.8 to the n, which means that this green -1 is not attached to the n at all. The n is not raising the -1 to that power. So just be aware that all the terms are going to be negative. And the next term is going to be 0.512, and it's kind of hard to see using the terms, but we can tell that this has to be a geometric sequence because you're just multiplying by 0.8 each time. So the first term is -0.8, and the common ratio is not -0.8. The common ratio is +0.8. Again, that negative is not raised to the n power. It's just hanging out in front. So r, you can see, is between -1 and 1. So it checks out. We can find the sum. The sum does exist. So the sum of all the infinite number of terms is equal to the first term over 1 minus the common ratio. That's the formula that we learned. The first term is negative 0.8. The common ratio is 0.8. And so we have negative 0.8 over 0.2. If we multiply both sides by 10, both sides of the fraction, we get 8 over 2. And we move this down a little bit. And so the sum is actually equal to negative 4. So there you go. So if you found that sum, excellent. So go ahead and try number 40. Number 40 has a purple star, so you can tell that something weird is going to happen. So try number 40, and when you come back, we'll do it together. Okay, we're back. So we can say, well, let's find some of the terms here. So we have 1 minus 10 plus 100 minus 1,000, and it continues indefinitely. So you can see that we're just multiplying by negative 10 each time. So the first term, well, we don't really care what the first term is because we can't find the sum. We can just say because r, which is equal to negative 10, is not between negative 1 and 1, the sum does not exist. So that's all you have to write. So if you got that right, excellent. Okay, so that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. But don't go before you get your homework. Here's the homework. Here's screenshot number 1 of the homework. And number 2. Number 3. 4. 5. 6. 7. And 8. So get that homework done completely and correctly. And remember, if you don't do the homework, it's 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.